Okay, welcome back everybody. Let's talk about physics. This is video lecture 5.1, and the reading that goes with it from Fundamentals of Physics is Chapter 5, Section 1, which is entitled Newton's First and Second Laws. So first let me try to give you the big picture for what we're doing now, because we're doing a pretty significant shift of gears, you might say. In the first chapters, up to through chapter 4, I will remind you what we have been studying is that part of the study of motion that is called kinematics. And remember, kinematics is merely, the purpose of it is to explain or describe, I should say describe, how a particle is moving. Just describe how it's moving. Now, of course, we've learned that when a physicist says describe how it's moving, we mean a lot more than just, oh, look at that pretty particle moving, isn't that nice? We use a lot of mathematics, and we defined a lot of quantities: position, displacement, velocity, acceleration, all defined by us as physicists to help us describe a particle's motion. That's what we have been doing. Here comes the shift of gears, because we're now going to start and look at a deeper question. Now we're going to ask, why does a particle move the way we observe it to move? Why? More than just how, we'll still do that, but now we'll also ask why. And a why question is a pretty deep question, right? What causes a particle to move the way we observe it to move? That field of study, that part of the study of motion that looks at the cause of a motion, is called in physics dynamics. So we are now moving from kinematics to dynamics. We'll still use what we studied in kinematics, but now we're going to add new ideas. Dynamics is the field we're studying. Okay, a little more about setting the stage. To answer a why question, to figure out what's causing motion, as I said, is a bit more deep, more fundamental. And we are going to have to, for the first time in this course, introduce what are called laws of physics. We had no laws of physics in kinematics. We had merely definitions. We defined what we meant by position and displacement and velocity, both average and instantaneous, and acceleration, both average and instantaneous. We just defined those things because we found those definitions to be useful. Laws of physics are different. Laws of physics, generally speaking, are first hypothesized by one or more people and then put under experimental scrutiny, tested and tested and tested by experiment after experiment after experiment. And we learn by these experiments the limitations of these hypotheses and so forth. And only those hypotheses that have been tested countless times and which we have studied and learned as much as we possibly can get to be called laws. Okay? And we're going to now introduce what are called the laws of motion. And they are due to Sir Isaac Newton, who lived in England in the 1600s, basically. And he wrote a famous book called the Principia Mathematica, in which he stated, amongst other things, these so-called laws of motion. We are going to use those laws of motion to explain why a particle moves. But it's going to take a lot of practice. We're going to have to build up the ideas bit by bit. So let's get started. First, I am going to start with a couple of, I'll call them definitions, although they're really nothing, really more just like descriptions. But we're going to need one key new idea to study dynamics. And here we go with our first definition. We are going to define a quantity in physics known as force. Now that's a rather everyday word, and everybody has an intuitive understanding of that, force. However, in physics, we have to be careful, and we have to be specific, and we have to be systematic when we use this idea of force. And so it may surprise you a little bit to learn that I don't really have a great foolproof definition of force for you. I'm going to give you just a description of it that will work, that will serve our purposes. Okay? Force is an interaction between an agent. The agent is the thing that's exerting the force, and an object. An object is the thing that experiences the force that can change the object's velocity. I'll say it again. Force is an interaction between an agent and an object that can change the object's velocity. All right, so it's an interaction that can change velocity. Force is a vector quantity. That's very important to understand. So it has a magnitude, which of course is the size of the force, how big is the force, and it has a direction. In what direction is the force acting? And it's got to have a unit of some kind. In the SI system, in deference to Sir Isaac, the unit of the force is called the Newton. And the symbol for that unit is a capital N. Or when you write out the name of the unit, you write Newton, and you don't capitalize the N at the beginning, because that's not his name. It's not a person's name, that's the unit, Newton. So the SI unit of force is called the Newton. Now, I've given you my description of force. You'll find others. A lot of high school physics textbooks will describe a force as a push or a pull, because you have an intuitive understanding of that, and that will work pretty well. And I don't have any qualm if that's how you want to think about it. Right? When one thing pushes or pulls on another thing, the first thing is exerting a force on the second thing. We're going to spend a lot of time in the next couple of chapters practicing identifying when one thing is pushing or pulling on another. One way, in a very practical sense, that you can detect at least a pulling force is this device right here. It's called a spring scale. It's got a spring in it with a housing around it, and it's been calibrated. And on the left, it's the SI unit of force, the Newton. And all you got to do is have something pulling on this hook at the bottom. And like I say, it's been calibrated. We won't go into how they did it, right? But if there's a pulling force pulling on the spring by means of pulling on this hook, then you can see how big the force is by seeing that pointer and seeing what it says in newtons. So if you have a spring scale handy and something is pulling on the hook of it, you know there's a force pulling on the spring scale, and you can even read what its value is, its magnitude is in newtons. All right, let's go to our first animation for this chapter, in which I want to demonstrate what I mean by my description of force as an interaction between an agent and an object that can change the object's velocity. I want to show you an animation where a force changes a particle's velocity. So let me transition now to a Wiley Plus animation. And what you have here is, what we're going to show you is an experiment that's going to be performed in a reference frame way out in deep space. Remember what a reference frame is from the last section of chapter 4? It's any set of axes, X, Y, and Z, and a time measurement device for making position measurements. My reference frame just shows an x-axis because we're going to have one-dimensional motion in this animation. And we have an object, a particle. It's that blue square, which represents some kind of a box that we've got out. And we've got it out in deep space, hence the black background. And the reason I'm imagining the experiment out in deep space is because I don't want to be distracted by extraneous pushes and pulls that you have to deal with when you're on Earth's surface and can complicate things. So let's imagine this experiment. Since we're going to run an animation, we can create it however we want. Let's imagine we've got our box out in deep space. All right, and when I run the animation, as you will see, here's what's going to happen. Let me take, if you can see there's a blue arrow pointing to the right. Let me take my mouse and mouse over it. I'll click on it here. All right, and now you see the letter F arrow appears. F is going to be one of the common symbols we use to represent a force. And since force is a vector, Note the representation is F with an arrow on top. That's what that blue arrow is representing. A force, a pull. Something is pulling on this box. And the arrow shows you the direction. It's pulling in the plus X direction. And it's pulling at time 0 when the animation begins, and I'm going to run the animation. Now you can see there's a hint of another arrow that's going to be present. It's the red tip there. A red arrow is going to appear that represents the velocity, not a force, velocity of the box out in deep space. So I'll play it a couple of times. First, I want you to focus just on what the force is doing. You can see the force is acting by pulling on the box in the plus X direction here initially. Now let me run the animation. Notice there's a timer to T. Aha, the blue arrow disappeared. How do we interpret what that means physically? It means the force went away. Whatever was pulling on that box stopped pulling. When did that force go away? Well, we can slide the slider a bit and see if we can figure it out. Oh, there it was. And there it went. Aha. At t equals 10 seconds, it went away. So the force was acting, pulling on the box between t equals 0 and t equals 10 seconds. And afterwards, after t equals 10 seconds, and until the end of the animation, in which it completely disappears at t equals 25 seconds, no force. So the force acts for the first 10 seconds. Now I'm going to reset, and I want you to watch what happens to the velocity vector, the red arrow. Look at that. It's getting longer and longer and longer. Now what's happening to the velocity vector, the red arrow? Notice the red arrow, the velocity, is not changing anymore. So for part of the animation, the velocity's changing, i.e. it's increasing to the right. You can see it there, increasing. Up to 10 seconds. Then after 10 seconds, the velocity is constant. Why did the velocity change that behavior? Apparently it was because of that force. In the first 10 seconds, a force acted and the particle's velocity changed. After that 10 seconds, the force stopped acting and the velocity was constant. Well, that is just what I described as a force, an interaction that can change an object's velocity. Okay, so far so good, I hope. Now, let's come back to an entity that was talked about a bit in Chapter 1 when we talked about just units. But we need to come back to it now as we study dynamics. And that is the concept of mass, M-A-S-S. Okay? Mass, what is that in physics? What does it mean? Okay? Here's another thing that, perhaps surprisingly, physicists are still discussing about how to come up with the best definition. So all I'm going to give you now is a description that will serve our purposes. Okay? And I'll have to even describe the description. But it goes like this. Mass, that property of an object known as mass, is a measure of an object's inertia. You might have heard of that word inertia because that is used sometimes in regular conversation, but in physics it has a specific meaning, as I will mention. Nevertheless, that's how we're going to describe mass, a measure of an object's inertia. Now, mass, good news, not a vector, it's a scalar. There's no direction to mass. As I hope you know, the SI unit of mass is the kilogram, kg. And now what do I mean when I say inertia? I said mass is a measure of an object's inertia. What do I mean by inertia? Inertia is the tendency for an object to resist changing its velocity. The more inertia an object has, the more it can resist changing its velocity. Intuitively, you know that a 747 airplane has more inertia than a bicycle. A 747 airplane can resist changing its velocity more than a bicycle can. Okay? Mass is a measure of amount of inertia. So a 747 will have more mass than a bicycle. You'll even hear people say very basic things, like mass is just a measure of the amount of stuff, the amount of material. In this course, that kind of thinking will generally not get us into any trouble. In more advanced physics, we'll have to be a little more careful. If you want to know, just for fun, but we won't actually use it, there was a recent article in a journal called the American Journal of Physics. It's just about a year old now, that article, where the author, Eugene Hecht, a well-known textbook author, physics professor, wrote an entire article about all the bad definitions of mass that are out there in the physics community. And Hecht's recommendation for the definition of mass, I will just tell you to whet your appetite, not that we will use this definition in the class, is the following. The mass of any object at rest is a measure of the amount of energy that went into creating that object as it exists at that moment. Of course, that includes this concept of energy, which we are not even remotely ready to define. So that's one of the reasons why that more formal definition isn't going to help us. We will stick to our description here. Mass is a measure of an object's inertia. The more inertia an object has, the more it can resist changing its velocity. Mass is a scalar in kilograms in the SI system. Okay, so those are just some ideas. Here comes the first law. In fact, we call it Newton's first law of motion. Haha. And we're just going to state it. It starts out as a hypothesis back in the deeps of time in the 1600s from Galileo and Newton, and has been tested and tested and tested, and so has been raised to the rank of a law. And it goes like this. Okay? Newton's first law of motion. If the net force acting on an object is equal to 0, then the object's velocity cannot change. You may have heard other wordings of this in a physics class in the past. Okay? I want us to stick to this because I want this idea here to be as basic and as clear as possible. Okay? All right. Say it again. If the net force acting on an object is equal to 0, then the object's velocity cannot change. I do need to emphasize the word net in that expression. Net, of course, is another way to say total. Or another way to say sum, add. All right? And remember, force is a vector. It could be that an object has multiple forces, multiple things that are pushing and pulling on it. And so what you have to do is you have to take all those force vectors and you have to add those vectors, vector addition, chapter 3, to get the total or net or sum of the forces and see what you get then. And if what you get is that the total or the net or the sum of the forces is equal to 0, then the object's velocity cannot change. That's what Newton's first law says. Let me go back to my animations here, and let me show you another one. Again, a reference frame out in deep space with our box, that's the blue square, and I'm going to run the animation. You can see the blue arrow. There is a force in the plus x direction. In this animation, it's labeled F1 arrow, and the red arrow is going to be the velocity. And I'm going to run the animation. First, I want you to focus on the force situation. F1. Aha. What happened? Let's pause it. At t equals 10 seconds, did you observe what happened? I had the force F1 in the positive x direction, and then at 10 seconds, all of a sudden, another arrow, blue arrow, pointing in the negative x direction appears. That represents a second force. Something else is now pulling on the box, and it's pulling in the negative x direction. And if I can mouse over it, there we are. You'll see it's labeled F2. And when you draw force arrows, you need to draw them with a consistent sense of scale, because the length of the arrow represents the magnitude, in this case of the force, in newtons. And so if assuming these are drawn to scale, you might notice that the F2 to the left and the F1 to the right look roughly like they have the same length. They just happen to point in opposite directions. And that happens to be true in this animation. F1 and F2 are force vectors in opposite directions that have the same magnitude in newtons. Right? Talking about a force. So the magnitude would be in the unit of newton. So before 10 seconds, I have one force, F1 to the right. Notice the velocity. Now let's look at that. Let's run it for 10 seconds. The velocity is definitely changing. Now, pause it for a minute. Now the second force has appeared, F2, and I'm telling you that it has the same magnitude as F1, but exactly opposite direction. So here's a question for you. If F1 and F2 have exactly the same magnitude and exactly opposite directions, what is the net force on this box, the total force? Did you say 0? You add the vector F1 to the vector F2, equal magnitudes, opposite directions, the net force is 0. Doesn't mean those two forces have disappeared, but their total is 0. And if the net force is 0, Newton's first law tells us the velocity can't change. So after 10 seconds, the net force is 0. So after 10 seconds, that velocity vector, the red arrow, had better not change. And you can observe that the red arrow no longer changes. So that's demonstrating for you Newton's first law. When the net force is equal to 0, the velocity cannot change. Okay? That's the key takeaway from Newton's first law. All right, now here come some more ideas that are important for what we're going to be doing in dynamics. It is the distinction between two classes of reference frames. Again, here we are with reference frames, a set of axes used for making measurements. And we're going to categorize all reference frames as far as the field of dynamics is concerned. All reference frames go into one of two categories only. There are only two possible categories, and every reference frame goes into one or the other. These categories are called inertial and non-inertial reference frame. Okay? So as far as we're concerned in dynamics, every reference frame is either inertial or non-inertial. And it can't be both. All right? It's either one or the other, and we have to be able to make sure we can identify which it is. So let's talk about these kinds of reference frames, and then I'll try to explain why it's important to distinguish between the two kinds of reference frames. First of all, what do we mean by an inertial reference frame? Inertial reference frame. By definition, a reference frame is inertial if it is a reference frame in which Newton's first law is valid, is true, by observation, like the reference frame in deep space I just showed you. In that reference frame in deep space, we observed that when the net force on the box was equal to 0, the box's velocity did not change. So by observation, that reference frame in deep space obeys Newton's first law. Newton's first law is valid. And so by definition, that reference frame by observation, is an inertial reference frame. Okay, well, now we know how to identify an inertial reference frame. We do an experiment and see if Newton's first law is true. And it either is true or it isn't. And if the experiment we do in the reference frame shows that Newton's first law is true, then we categorize that reference frame as being inertial. Conversely, if we find a reference frame in which Newton's first law is not true, we call that reference frame non-inertial. And yes, there can be reference frames where Newton's first law isn't true. And Newton knew this. He recognized that this could be the case. Let me show you with an animation. Okay? All right, now, what I need to do here, bear with me please, just one moment. I need to get another animation here. Okay. So now let me show you. All right, now you see another animation that I want to show you. There's a lot going on here, So let me explain what's going to happen, what you're going to see. You see this platform, which is this kind of light pink or this pinkish rectangle sitting in the middle of the field of view. That's just a platform that has its lower surface lubricated, greased, so that it can slide on this tabletop with no what we call friction, which is an intuitive word for now that I think you understand. It will slide with no friction because we've greased it, we've lubricated it. On the left end of this platform, we've connected a spring, or one end of a spring. The other end of the spring is fixed to a wall on the left. On the right end of the platform, we've connected the end of a different spring, another spring, and its other end is connected to another wall. You can see the two springs there. I've also got a reference frame called frame A that is shown by the black arrows labeled XA and YA. That's reference frame A, and it's going to be fixed relative to the Earth, fixed relative to this tabletop. And then I have a block right there, that small red rectangle with the black dot in the middle. And it also has had its lower side lubricated so that it can slide on top of that platform with no friction. And the black arrow just shows you the x-coordinate of the block as measured in frame A, because it comes out from the origin in the x direction from frame A. When I run the animation, you're going to see that the lubricated platform is just going to oscillate back and forth because of the springs. I want you to focus on the red block, the small red rectangle. Okay? Okay, so the platform is oscillating underneath the red block. That's all, right? And reference frame A is not moving because it's fixed to the Earth, and that's where we are. Did you notice that the red block, as observed in frame A, was not moving? Okay, so what's the acceleration of the red block? Review question. Think about that a second. Pause the video if you need to. As observed in frame A, what's the acceleration? What can you tell me about the acceleration of the red block? Okay, did you say the acceleration was 0? The red block is just sitting there, not moving. So its velocity is 0, and its velocity isn't changing. So its acceleration is 0. Or to say it another way, its velocity is constant at the value 0, but constant. Now I contend that reference frame A fixed to the Earth in this animation is an inertial reference frame. So Newton's first law must be valid. By observation, the velocity of the red block is constant. So by Newton's first law, the net force on the block must equal 0. Now we just got started thinking about forces, but let's just see if we can intuit. What forces do you think are acting on the red block as we observe it here? Well, there's the one from Earth pulling downward. We call that a gravitational force. So there's a downward gravitational force on the red block from Earth. But that can't be all, can there? Because then the net force wouldn't be 0. But we know the net force must be 0 because Newton's first law holds. If there's a gravitational force directly down, there must be another force directly up of equal magnitude so that the net force is 0. We will learn later in this chapter what that force is called. I'll tell you now, it's called the normal force from the platform. But point is, net force on the red block equals 0. Velocity of the red block is constant. Newton's first law, good to go. All right, now I'm going to reset the animation, and I'm going to unclick this box. Now we, the observers, are going to be in frame B, reference frame B. What is reference frame B? First of all, you'll see it drawn with blue arrows labeled XB and YB. And reference frame B is sitting on the platform. It's nailed down to the edge of the platform and does not move relative to the platform. And we're now going to be observers in frame B, as if we were sitting on the platform. I wonder what we will see. Let's run the animation. We see the red block going alternately towards us and away from us, and we see the right and left walls going alternately towards and away from us, and we see reference frame A moving toward and away from us. Everything is oscillating when observed from frame B, especially, let's run it again, the red block. Its x-coordinate, look at that black arrow. That black arrow is getting longer and shorter, and longer and shorter. The x position of the red block is oscillating, which means it has a velocity. And in fact, its velocity is always changing. So as observed in frame B, the red block is accelerating. Okay? All right. Now, let's see if Newton's first law is valid. Newton's first law says that if the net force equals 0, the velocity cannot change. So let's kind of reason our way beyond that a little bit. What if the velocity is changing? That's what's happening here. Then the net force must not equal 0 if Newton's first law is going to be valid. I contend, however, that the net force on that red block is still 0. Okay? Now we're going to have to practice with forces, but let's explain why that's true. Of course, we've got the gravitational force down. That doesn't go away. And we've got that normal force up from the platform. That doesn't get affected, and those two balance. So the net force from them is 0. And nothing else is pushing or pulling on the red block. If you want to tell me something else is pushing or pulling on the red block, you must be able to tell me exactly what the agent of that force is. The agent is the actual physical thing that pushes or pulls. And except for gravity, which is a special force, anything that wants to push or pull on that red block has to be touching it. Is anything touching that block besides the platform? And we've already accounted for that force, the normal force. No, there are no other forces. The net force on that red block is 0, as observed in frame B, and yet the block's accelerating. In frame B, Newton's first law isn't true. As I said, Newton knew there would be reference frames where the laws of motion as he was writing them weren't valid. Frame B is 1. So frame B is a non-inertial reference frame. So I'm showing you examples for now, perhaps cooked up, but you could do an experiment like this in a lab. I'm showing you examples of inertial and non-inertial reference frames. So now let's go back to our notes and make a couple more comments. Things that are really important to note for our work in solving homework problems and talking about dynamics in class. First, any reference frame fixed to Earth is going to be taken to be inertial. Yes, technically, very technically, it's true that Earth itself is only approximately inertial. And if you have certain situations, you can see deviations from Newton's first law. We won't worry about those in this class. As far as we are concerned, solving any homework problems, doing any example problems in class, any reference frame fixed to the Earth will be inertial, and therefore Newton's first law will be valid. And his second law, which we're going to talk about in a minute. That's the reference frame A in the video I just showed you, the one that was fixed to the ground, and the one in which we saw Newton's first law to be true. All right, so just remember that. It's very important. Any reference frame fixed to Earth, the ground, we will take to be inertial, and Newton's first and second law, valid. Here's another idea. Any reference frame moving at constant velocity relative to Earth will be taken to be inertial. Constant velocity. Now, I didn't have an example of that in my animation I just showed you, but you could imagine. You've got the ground, and maybe you've got train car on straight train tracks and it's just rolling along at a constant velocity, that's another reference frame, and it would be moving at constant velocity relative to Earth. And if you studied motion from that constant velocity frame, you would find Newton's first and second laws work fine. Okay? So any reference frame moving at constant velocity relative to Earth is also inertial. However, any reference frame that is accelerating relative to Earth, keyword, accelerating relative to Earth, is non-inertial. Newton's first and second laws aren't valid the way we've written them, and we won't use them. So we will never do a homework problem or any kind of dynamics analysis from one of these non-inertial reference frames. We will avoid them judiciously. Frame B in the animation I just showed you was an example of a non-inertial. Because of the springs that were causing frame B to oscillate back and forth, frame B was accelerating relative to the Earth. And we saw in frame B that Newton's first law wasn't valid. Okay, so we're always going to be applying Newton's first and second laws, doing dynamics in what are called inertial reference frames, one fixed to the Earth, the ground, or a frame moving at constant velocity relative to the Earth. Okay, one more key idea, but it's a biggie. Another law of physics that we need. It is the key one, in fact. No doubt about it. The key law when studying dynamics. Okay? And of course, it's called Newton's second law of motion. We've already stated the first law. I'm now going to state the second law, using just some words first, but then it's going to be stated really in equation form. First, what I want to emphasize is what the second law kind of is fundamentally at heart. Newton's second law is a relationship between cause and effect. That's a very scientific idea, right? Cause and effect. A lot of times in science, we are wanting to find out what's the cause of an observed effect. And it can be subtle to sort out what's causing something to happen, right? So this turns out to be Newton's second law, a cause and effect relationship. That is to say, when you have a net force acting on an object, that net force causes an object with some mass m to accelerate. A net force acting on an object causes that object to accelerate. So cause is net force. Effect, acceleration. Okay? And so I'm going to write that cause and effect relationship, Newton's second law, in an equation form. And it's pretty famous, and if you studied high school physics, did an AP physics class or an IB class, you've seen this before. But we're going to spend a lot of time practicing with it. And it says, and I write it this way, which is not the way most books do, because I want to emphasize the cause and effect relationship. And so I want the effect, the outcome, isolated by itself on the left side of the equal sign, which is kind of how we intuitively think about effect. The outcome, the output, it's on the left side of the equal sign. And the law says that the acceleration vector that results for a particle is equal to the net force vector acting on the particle divided by the particle's mass. Acceleration equals net force over mass. Very simple algebraically, but conceptually can get very subtle, or at least things can be overlooked. For example, subscript on the F, net. It must be the total force acting on a particle, and that means vector addition because forces are vectors. So we're going to have to add vectors like we studied in chapter 3 by components. And the acceleration is inversely proportional to the particle's mass. So if I apply a given net force to a 747 and a same net force to a pencil, the object with the bigger mass will have the smaller acceleration. In this case, the 747 will have the bigger mass, and so it will have the smaller acceleration. Now, the way we're going to use this statement of Newton's second law in solving problems is by writing it in component form, because it's an equation with vectors. So everything has to be done by components. And I can't emphasize that too strongly, how important it is to deal by components with Newton's second law. For x components, we have the expression here on the left. The x acceleration of a particle is given by the net of the x forces divided by the mass. You have to add up all the x forces only, then divide by the mass, and you'll get the x acceleration. You cannot include y forces when you're trying to find the x acceleration. Similarly, for y components, the y acceleration that a particle has is given by the net y force acting on the particle divided by its mass. And only the y forces, but all the y forces. You don't ever include an x force when you're trying to find the y acceleration. You can't mix the components. Okay, so that's Newton's second law, a statement of cause and effect. We are going to be spending a great deal of time practicing using that. We're also going to be spending a good bit of time talking about some common everyday forces that we're going to find acting on particles. So that's what we're going to be turning to next. But the next video, which is going to be our in-class video for Thursday, is going to be practicing with the first and second laws. But for now, that's all for this video.